isn't it? And if this magnetic field, by the way, begins there abruptly and uniformly, it's going to go spiral down. What's it going to do? Come back out. It's going to do 1/2 of a circle and come back out, isn't it? Yeah. It's going to do this. And then it'll come back out, yeah, straight, right? That's crazy. If it's inside that magnetic field all the way when it's moving, of course, it's just going to spiral around and around and around in a circle, right? Do you suppose we use this in particle accelerators like cyclotrons and synchrotrons and the Large Hadron Collider? We use magnetic fields to make them go in circles? Yeah, this is like all the time we do this, yes. All right, electron is going to do the opposite, right? So let's do it. Index fingers that way, magnetic field out of the page. It's down, but it's negative down, right? It's so down, it's negative down. So it's up, right? Yeah, it goes up.
Does that mean you get an opposite magnet on the other side? You can make them go between them?
Well, yeah, you could. I mean, but you just have the same magnet, right? You just have this guy and it would just go boom, 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 like that, right? Yeah. Huh? Oh, just set it on my attendance binder right there. All right, next one. Uh-oh, electron. Now it's going this way. Magnetic field's out of the page. Our thumbs are up, but it's negative up. It's down. It's going to curve. Proton. Down. Into the page. It's a proton. No surprises here. It's positive, right? No reversals, right? So isn't it going to go, it's going to go that way, isn't it? Isn't it? Yeah. Okay, electron goes that way. Magnetic field is into the page, yes? Thumb is up, but it's negative up, so it's down. All right. So, I don't know all that much about the Large Hadron Collider, but just notice that the point here is that they've got these ring-shaped things, and some of these things actually feed particles into the main ring. Notice that the ring is a big ring like that. Those things, basically, they have superconducting magnets, right? These are magnets. Once you get the current going in the magnet, right, that it becomes and then you make it a superconductor. The current flows forever. There really is zero resistance, right? They can generate tremendous magnetic fields, and those superconducting magnets actually make the particles go around in circles, right? And I asked my organic chemistry professor, because he used superconducting magnets to do, I believe, nuclear magnetic resonance to identify organic compounds, right? And the story he tells is that his dog walked into the room, I think his wife brought his dog or something like that, and these huge superconducting magnets are just tremendous, and they have these enormous magnetic gradients, okay? And you really can only pick something up if you have a magnetic gradient. Okay? It's got to be stronger in some location and weaker in another, right? So if I've got a piece of metal here, right, and I've got a magnet here, this is the North Pole, say, right? This side's going to be the South Pole, this will be the North Pole of the induced magnetic field, okay? But if the magnetic field is uniform, then this guy is attracted to this guy with the same force that this guy is repelled by this guy, because the magnetic field doesn't drop off with distance. But if it's really strong, if the magnetic field is much stronger here and much weaker here, then this force of attraction is stronger than the force of repulsion. And that's the way it normally is, right? So these giant magnets that he had generated this enormous magnetic field, right? And the dog walked into the room, was wearing a metal collar, like one of those chains, and it picked the dog up from the, like 10 feet away from this magnet, slammed it against the giant superconducting magnet, and was killing the dog. I mean, it was like the chain was crushing the dog's throat. The dog couldn't breathe, right? And they couldn't get the dog off the magnet. And so the guy runs up to the magnet and just goes boom and shakes it. They don't like to be shaken, right? That makes them not superconduct, right? And so all that current and all that stored energy in the magnetic field just suddenly turned into heat, and then of course then the magnet was really not a superconductor, and all the liquid helium vents through the ceiling, and dog falls down and is okay. Dog. The dog's okay. Yeah, yeah. Everybody's like, dog? Is the dog okay? No learning whatsoever about magnetic fields. But anyway, I asked him. I said, how do you get the current flowing in a superconducting magnet? And this is possibly the most interesting thing we'll talk about. I thought this was cool, right? What they do is they've got, say, a coil here, a superconducting magnet coil like that, and what they'll do is they'll take a small part of this coil and they'll take it outside of the, like this. I'm trying to draw this so it doesn't look bad, but anyway, let's not worry about this, right? Okay, so what they'll do is they'll stick this stuff in the liquid helium. This part is superconducting. Then they'll attach a power supply from here to here, and they'll pump the current up there, and they'll get it up as high as they can. At some current level, the superconductors will break down. This part is not a superconductor yet because it's still warm. Okay, warm superconductors are not superconductors. They're just like, actually they're more like a ceramic cup than anything, right? And so they get the current going in this, they get this superconducting, right? They crank the current up really high. Then all they do is they pour liquid helium over this part of it, right? Which cools it down, and it becomes a superconductor. And as soon as the entire thing is superconducting, the current just keeps going, and it goes forever and ever. It really is frictionless. Isn't that wild? That's a wild thing, right? Because I was like, how do you do it? I was picturing like they would like get the current going and then connect it, together, and or I don't know. And so as soon as it becomes superconducting, the power supply has just like there's nothing. It doesn't do anything, right? It's just like there it is. Isn't that wild? Okay, so here's the ghostly image. You can't see this, right? But it's under the ground like that. It's giant. It's kilometers across, right? This is inside the tunnels. This is where the particles go inside that tube there. And there's giant magnets that are generating magnetic fields there. And yeah.
Are you not dealing with plastic?
Around these magnets, I don't know what the gradients are, but yeah, for sure you want to make sure that you don't wear magnetic objects near these things, right? Okay. Okay, so let's try some of the number ones, right? What's the force acting on a proton moving 2.5 times 10 to the 8th meters per second, which is very close to the speed of light. The speed of light being 3 times 10 to the 8th, right? 0.35 Tesla magnetic field. There's the charge. You can look that up. The mass of a proton you can look up in the data packet. Charge you can look up. Calculate that. Put that number on a whiteboard. Show me the answer. Yeah. Well, now you should have a marker, shouldn't you?
I should, but is E the mass?
I would like to fix it.
No, that's like a bad one. Yeah, I've got some you could buy.
A good one? Or the one you're showing ran out like 3.
Did it? I got another brown one. Did the brown one run out really fast?
Actually, the brown one was good. I bought a black one. I may have left it off. Like not all the way.
I did just that massive proton.
Yeah, that's right.
Aren't the mass of a proton and electron the same?
No.
Is that
The charge is the same as a proton and electron, but a proton is like 2,000 times more massive than an electron.
2,000.
I didn't know.
Yeah, what units would that be? It's a force, so it's going to be... Is that minus 11? Is that important? Yeah, that's right.